Hello, everyone. So this is video 9. I'm gonna pick up, by lecturing from the second page of the notes. So we're gonna talk about the derivative as a rate of change, kind of in the middle of the page, where we left off on the end of video 8. So let's just review a few things that we've kind of been talking about throughout the class, off and on in some ways. And they did rear their head in video 8 again when I was talking about position, velocity, and acceleration. So this idea that, namely the idea that the derivative is a rate of change. Excuse me. So y equals fx, a function. The derivative of f at x equals I, right? So that's f prime at I, right? So what does that mean? We have different ways of interpreting this. So the kind of geometric interpretation is that this is the slope of the tangent line to the graph of f at x equals I, right? But we have also a practical kind of physical interpretation, and this is the instantaneous rate of change of the quantity y equals f at x when x equals I. Exactly when x equals I. So there are two interpretations, and both of these can be used kind of together to conclude some interesting, or to make some interesting approximations about a quantity you want to understand. So just as an example, again, keep coming back to this example, it's the easiest one, but we'll do some more examples today that are, shall I say, maybe a little, if you like business, a little more up your alley maybe. But just to keep coming back to it, so we can have a function s of t, which is the position of a car at a time t, right? And then this s prime of, say, at a, this is the same thing as the velocity of a, right? So this is the velocity of car at t equals a, and that is the instantaneous rate of change of the position with respect to the car at that moment, t equals a. So that's like, if that number is positive, that's what your speedometer is reading at that instant. So instantaneous, it's a long word, rate of change of the position of the car with respect to time at t equals I. So we talked about this in like the very first week. We were trying to, like, what does it mean? What does the derivative mean? How do we kind of think about it practically? And this is the example we used, like, okay, the slope of the tangent line to the position versus time graph. That's exactly the rate of change of position versus time at that moment, and that's the velocity of the car at that moment. And it's what your speedometer is reading if that's a positive number. Okay, so but this can be done, I mean, this idea of instantaneous rate of change, like I was saying above, can be done for any abstract quantity, right? It's not just position, velocity, and physical stuff, but for things from economics and other things as well. So that's what I want to play a little bit with today, and see what trouble we can get ourselves into with these ideas. So one of the things we're going to be playing with today is using the derivative to estimate the change in a quantity we're interested in. So, oops, sorry. So this is a little example. So since f prime at a is the instantaneous rate of change, I'll just write instant or inst for instantaneous. So I'll write the too long a word. Rate of change of f at x equals a we can use it to estimate the change in the function f y equals f of x as x changes 1 unit from x equals a to x equals a plus 1, say, okay? Now, you'll see why you want to do this in economics in a moment. So what I'm saying is we can do the following. So we have the approximation f of a plus 1 is approximately equal to, with approximately equal to, you do these like little squiggly equals, squigglies, f prime at a plus f at a. All right, now let me put this in a box and kind of explain to you why this makes sense. We'll call this star. So in other words, it says that we can estimate f of a plus 1 by taking the derivative and adding the value of the derivative plus the value, the original value f of a. So where this comes in useful is like, you know f of a, you can find f prime at a, and you want to have an estimate of f of a plus 1. Okay, we'll see this in examples. So the equation star, what is this doing geometrically, is estimating the value of fa plus 1 by going 1 unit along the tangent line from x equals a to x equals a plus 1. So let me draw a picture of what this might look like. You'll see that this is not, you'll see that this is not a bad approximation. It's pretty good, unless your function is really, really badly behaved. So I'm going to kind of produce the picture that's in, we try to reproduce the picture that's in the notes a bit. Okay, so here we have the point A, and just to blow it up a bit so you can see and I can see, and I found that picture in the PDF was a little hard to read. It's a little fuzzy, but I'll try to make this a little less fuzzy. So there's their point AF at A, and I can draw the tangent line. Oh, that was a bad tangent line, sorry. That's a good one. Perfect. Okay, I can draw the tangent line, the red line there, to the graph at AF at A. And now, right, what I really want to know is I want to know this blue value here, right, this f of a plus 1. But say, like, for whatever reason, I can't compute that directly, right? Maybe, you know, it's like, think about this problem with a car, right? You're traveling along, you know your speed at a certain point, right? You look at the speedometer and you want to kind of have an idea when you're going to get to the next exit, right? Well, you might have to speed up or slow down between there and the next exit, but if you just took the speed you were traveling with at that moment, you could use that to estimate, right, how long you travel in the next minute. And that's kind of what we're doing. So what this value, I'm going to use a different color. So we want to know f of a plus 1, but we can instead, for whatever reason, we don't know how to get it exactly from the function, but we can get it from the tangent line, because tangent line is easy to work with. The slope of the tangent line is f of a, f prime of a. We just move along 1 unit. So then we've gone, this distance here would be f prime of a, the slope times 1, right? Plus the point you started with, which is f of a, so plus f of a. So that's this distance here. So the height there. Sorry, that's the height of this point here. Right, so just moving along the tangent line, 1 unit, the slope of the tangent line is f prime of a, right? You move 1 unit to the right, so you move up by f prime at a times 1, which is f prime at a, plus f of a. And that gives you this point, the height of this point on the tangent line. And, it's not perfect, but it is a decent estimate, or y times 1. It is a decent estimate of what you want to know f of a plus 1. Okay, so that's the idea behind this kind of using the derivative as and the rate of change at the point f prime at a, at the point a, f at a, to estimate the value 1 unit later. Okay, so where does this come up in applications? Like I give you this silly car thing, but let's do something a little more serious. So in economics, you have these kind of marginal concepts. And if you're interested in business, this will be good, maybe important for you. Okay, so you have different functions. So cost function, which we'll denote by C at x. And so this is the cost, say in dollars, of producing X units of whatever you're producing. It could be like bicycles, like maybe footballs, I don't know, pounds of meat, if you're, in the butchering business, what have you. So the cost of producing X units of some commodity. And of course, the exact units of this would be dependent on what the commodity were. It's the cost function. Then, of course, okay, so you also have a revenue function. R at x. And this is the revenue generated when you've produced X units. And then you have the profit function, which is the most important, right? Which is the cost, the revenue minus the cost, right? And we should give that a name, we'll call it P of X. Okay, so now the derivatives of these functions are the so-called marginal functions. And they have important meanings for reasons we'll see in a moment. So the derivatives of these functions are the so-called marginal functions. So the derivative of the cost function is marginal cost. Derivative of the revenue function is marginal revenue. And the derivative of the profit function is the marginal profit. Now, what these represent, like say, for example, with marginal cost, that's the rate of change of the cost when you're producing exactly X items. But that's not really how you use it. You can use these functions to estimate, say, in the case of the cost of producing one more item. It just as we did, just as I explained a moment ago, by going along the tangent line in 1 unit, by using that formula star that we had above. And I'll remind you. So these functions are used to estimate C of X plus 1, R of X plus 1, P of X plus 1, using the formula given in star above. So where did star go? There it is. Okay. So if we know the marginal cost, right? So if f is this cost function, right? You know the marginal cost when you've made A items, and you know the cost of A items, then the cost of making A plus 1 items is given by the marginal cost plus the cost of A items. And then that's why the derivative is referred to as the marginal cost, because it's thought of as estimating, you being used to estimate what it would cost to produce one more thing. So on the margin of what you've already made, what would it cost to make one more thing? And similarly for revenue, right? So if you're playing this game with revenue, the marginal revenue, the revenue that you get from making A things, plus the revenue, sorry, the marginal revenue when you've made A things, plus the revenue when you've made A things is approximately the revenue you get by making one more thing. And same thing for profit. So these are called marginal quantities because they estimate on the margins of what you've already done what the cost of one more thing, producing one more thing would be, what would the revenue from producing one more thing, what would the profit eventually be from producing one more thing, and so on. So for example, if we have produced X items, the cost of producing X plus 1 items is given by star to be approximately Cx plus 1 is approximately equal to the marginal cost plus the cost of producing X items. And thus, C prime of X is referred to as a marginal cost because we think of it as estimating the cost of producing exactly one more item by just rearranging. So if we just rearrange this equation here, I call it double star. If we rearrange double star, we would get Cx plus 1 minus Cx is approximately C prime of X, right? So the cost, So if you just rearrange that, you get the cost, the difference in cost of producing X plus 1 from X plus 1 to from X to X plus 1, that difference in cost is approximately the derivative or the marginal cost. So that's where the term is coming from. Okay, so let us actually do a concrete example. And so I should say, so similarly for the revenue and profit. And then we'll do a concrete example. So okay, I just need to take a quick break. I'll be right back. Okay, so I'm back. So let's actually do an example. So I'm gonna do the example at the bottom of page 2. Unfortunately, they didn't give you a ton of room to write, but you might want to do what I'm doing, write on a different piece of paper and kind of just include it with the PDF notes. So here's the example. So let C of X, my C's and my parentheses look a little too similar. Let C of X be the cost in dollars of producing X bicycles at some plant or something. And let's suppose that if we produce 60 bicycles, it costs $6,000. So that's the same thing as saying, for example, or i.e., the cost of 60, the cost function at 60 is 6,000. Okay, and that the marginal cost when we produce 60 bicycles is $65. And so now what we want to do is estimate the cost of producing one more bicycle. 61 bicycles. So that's what we want to do. Estimate the cost of producing exactly one more bicycle, 61, which is 61 bicycles. Okay, so we can use what I was just saying above. Where did it go? Double star, equation double star, right? Which tells us how to use the marginal cost to estimate the cost of producing one more bicycle. Once we know the cost of producing 60 bicycles, right? So we can estimate the cost of producing one more when we know the marginal cost and the cost of producing X bicycles. So we're just going to use that formula with X equals 60. So we will use formula double star. When X equals 60. Okay, so we get the cost of producing 60 plus 1 bicycles is approximately equal to the marginal cost when we produce 60 bicycles, plus the cost of us producing 60 bicycles. And so that's the same thing as saying the cost of producing 61 bicycles is approximately equal to, now what were our values for this? So this was $65 and this was $6,000. And so that equals $6,065. So sometimes it's nice to have a statement, like a formal statement when you're doing these problems. So the cost of producing 61 bicycles is approximately $6,065. Okay, so again, now you can kind of see like why you want to use this estimation. Like you know the cost of, you've produced 60 bicycles. You're wondering how much more money is it going to cost me to produce another bicycle? So if I make one bicycle, what's my total cost? So that's what we've computed here. It's it costs you $65 more to produce, approximately $65 more to produce another bicycle. So your total cost of producing 61 bicycles is $6,065. And that's the kind of thing where you don't know exactly what this value is until you've produced another bicycle. When you've actually gone and produced the other bicycle, you might get a slightly different value for this. That's okay. But this is just like kind of a back of a napkin calculation to give you an idea of how much it would cost you to produce that one more bicycle. And so it's like I was saying, it's like your speed, you're traveling 70 miles an hour, you're like you're 1 mile from the next exit. You could use that information to estimate like how long it's going to take you to get to the next exit, right? But you might not actually take you that period of time. So that's the kind of thing we're doing. And so you'll play with more of these ideas on your homework. Okay, so let me go to the next idea in section 1.8. And I won't do all the problems here because I've talked a lot about velocity and acceleration with you guys before. And so I want you to kind of see if you can do some of these on your own, and we can talk about it in the live meetings as well. Okay, so section 1.8. Again, more about rates of change. So there is another notion, or I should say another notion of a rate of change over a function y equals f at x over an interval a, b, and this is the average rate of change of f at x over AB. And so what is this? What is this average rate of change? So this is equal to the total change in f over the interval AB divided by the length of the interval, the b minus a, and as a formula, that's f of b minus f of a over b minus a. So this is average rate of change. Of f over the interval a, b. So I'll put that in a box for you. Now, this is something too that actually is very easy to compute, and it's something you can compute when you don't know the derivative, or you can't quite get the derivative. We won't do a ton I think with this for now, but it's good to be aware that it's there. So let me kind of give you an example of how you might think of this before diving into what's in the actual note sheet. So here's kind of an example. So remember, like, we are driving to New Orleans. This thing I keep coming back to. And our position versus time graph might look something like the following. So you kind of start very slowly, you speed up, get on the highway, there's a jam, you got to slow down, you come to a stop, speed up again, and then you get off the highway and you're done. And suppose because of the traffic or something that this takes you like 3 hours, right? So that's very unfortunate, but I've had worse than that. And the distance is approximately 150 miles, right? To New Orleans, depending on where you live in the Mobile area, right? Okay, so the question would be, I want to answer is like, what is our average speed? And this is something that you probably have thought about and maybe in practical situations. So what is our average speed during the trip? Over the course of our journey. So in the language, so we have our position versus time function, right? S of t is our position versus time function. And the interval here is 0, 3. So if you use the formula above, you'd have S of 3 minus S of 0 over 3 minus 0, which is just total change in position, right? Over the total change in time throughout this time interval that we were driving. So it's total change in position divided by total change in time. And so for us, so we can put these values in. So after 3 hours, we're 150 miles out. So it's 150 minus 0 divided by 3 minus 0 is 150 divided by 3. And that equals 50 miles per hour. No, sorry, miles per hour. Now, you know, right, that you weren't driving 50 miles per hour the whole time, right? Because you could, like I said, you kind of start off slowly, speed up, you hit some traffic. So you start off slowly, you sped up, hit some traffic, had to stop, sped back up again, and then got off the road, right? So, but it just tells you on average how fast you were going in those 3 hours. So that's what it means. That's why this average rate of change is total change of the function over the total change in the x variable over the length of the interval. And that tells you on average how that function changed from the starting point of that interval to to the end of the end point of that interval. So in this practical example, you see that if you took you 3 hours to cover 150 miles, on average, you're traveling 50 miles an hour. Okay. Now, however, as you should believe, right, that the average rate of change and the instantaneous rate of change will be quite different. So that's what I want to illustrate in the next example. So recall also that f prime at A is the instantaneous rate of change of x equals A, sorry, of f at x equals A. And this is often very different from the average rate of change. So like in the example above, right? Like I was saying, the average speed is 50 miles an hour, but we know that we are not traveling 50 miles an hour the entire time in the course of the journey. Sorry, Puccini came to visit. Hello, Puccini's. He needs to move. Yes. Yes. Put you here. That's good. Okay. So here's an example. So this is going to be more abstract. So suppose that we have a function, f at x is equal to 3x squared plus 2. And we want to do two things. First, find the average rate of change. Over the interval x equals 1 to 4. And the second thing is find the instantaneous rate of change. When x equals 4. Okay, so here we can do the following things. So for number 1, so average rate of change. So this is the total change in f over the interval 1, 4 divided by the length of the interval, so 4 minus 1. So that's f of 4 minus f of 1 divided by 4 minus 1. And now we just have to find these values. So f of 4, what was our f? Right, our f here is 3x squared plus 1. So this is 3 times 16 minus 1. Now watch your parentheses here. 3 times 1 squared is 1, right? Minus 1 all over 3. Now we have to do some algebra. And maybe I'll go down to the next page here. So we have 3 times 16 minus 1 minus 3 plus 1. Make sure you distribute this negative over in a good way, okay? Don't, otherwise you'll get some answer that'll be messed up. All right, so we see that the 1s cancel. And we're left with 3 times 16 minus 3 over 3. And notice that actually you could figure out what 3 times 16 is and subtract 3, but you can also divide the numerator by 3, right? And so you get just 16 minus 1. That's the slick way, so it's 15. So the average rate of change over that interval is 15. Okay, now compare it to the instantaneous rate of change. So I can just say the average rate of change over 1, 4, interval is 15. So now for the instantaneous rate of change, we have to compute the derivative. The instantaneous rate of change at x equals 4, we compute f prime at 4. So first we need to get the formula for f prime at x from the power rule. F prime at x, which is the derivative of 3x squared. Oh, it's 3x squared plus 2. Did I write that down right? Oh, sorry about that. Okay, so this is, okay, well, that actually does not affect things at all, but I should be careful about that. So there should be a 2 here. There should be a 2 here. They cancel. But we should try to be consistent with what's in the notes. Okay, so this derivative, again, is the sum rule and power rule. And so we get power rule is 6x, right? The 2 comes down, multiplies the 3. You drop the power by 1. The derivative of a constant is 0. So f prime at x is 6x. And therefore, f prime at 3 at 4 is 6 times 4 is 24. And that's quite different from what we found for the average rate of change, where the average rate of change was 15. There it is. And the instantaneous rate of change is 24. So actually, if you graph this, you can kind of, so with the car example, we kind of know why to believe that these are very different things, because your average speed is very, very different than your speed at any given instant, because you're starting and stopping, accelerating and deaccelerating at different times. Whereas the average speed, or the average velocity, is just the total, how far you've driven over the time that it took you to drive there, right? But how do you see in an abstract example why these things would be so different? Well, we can kind of draw a rough sketch. So this isn't part of the question, but I think it might kind of help to think about it this way. So we can draw a rough sketch to understand why these quantities are so different. So the curve, if you remember from basic kind of transformations, the curve 3x squared plus 2 is a parabola that's been kind of translated up by 2 and stretched. And so say here you have, maybe it's not as flat as that. So it's kind of stressed out a bit. So it's going to be up 2 units and kind of stretched. Okay. And so somewhere you have like here the point, say 1, and over here 4. And the curve keeps going up. Okay, so the derivative at 4, right? The instantaneous rate of change of 4 is the slope of the tangent line of 4. So it's the slope of that red line. So f prime at 4 is the slope of the tangent line to f at x equals 3x squared plus 2 at x equals 4. Now, and so that slope is 24. So we just computed that slope is 24. Now, what's the average rate of change represent? So let me draw the following. So here we have the point 4f of 4, right? And here we have the point 1f of 1. And I'm going to draw the purple line connecting those 2 points. And if you think about it, now in this picture, unfortunately, they're very similar, but the average rate of change is f of 4 minus f of 1 all over 4 minus 1. This is the slope of the purple line, which is 15. And I probably needed a little bit more accurate picture to show you this properly. Let me see if I can draw it a bit better. But the slope of the red line is steeper than the slope of the purple line. So the instantaneous rate of change at 4, right, is more positive, sharper than the average rate of change. And it's hard to see like the precise quantities without a proper scale, but that's the idea. So the slope of the purple line, right, is the total change, the slope of the line connecting these 2 points, right? This is the, I'm kind of going to be a crowded picture, but this is the total change in y over the change in x, which is 3. And so that's the average rate of change, and that's the slope of the purple line. Okay, so that's enough for now. We have a little bit more to do on the notes. I want to talk about a little bit more general approximations using derivatives, not just approximating one more unit, but an arbitrary number of units. And then we'll do some applications with velocity and acceleration and all those fun things. So thanks for tuning in.